All right, recorded is rolling. So it is Wednesday, December 14th. We're going to finish this midterm review today. So this is day 4 of this midterm review. We've been going over these conceptual questions. If you need one of these for whatever reason, got a couple extra copies up here. And yeah, we're about halfway through this one. Right. There was a faculty meeting this morning. Main thing they were telling us about was when we come back from the break, which is going to be January 5th and 6th. So the first couple days back are January 5th and 6th. They're technically part of first semester. I don't think you really need to worry about that unless you have like a schedule change or something. But all right, so here's what I was getting for the plan. Okay. You guys are going to be in your first period class pretty much all day, with the exception of they'll let you go to fifth period just to keep all the lunches on schedule. But then after lunch and after your fifth period class, you go back to your first period class for the last couple hours a day. Okay? Bring you guys bring those laptops. Right? Bring those with you, or some device so you can take a youth truth survey. That's going to be at least one of the hours. Right? Bunch of survey stuff. You guys probably remember that from past years. Right? Oh, there is a chance possibly you might get switched because, like, I know my first period class is mostly 11th to 12th graders, which 11th to 12th graders are going to get some presentation, but I do have a handful of 10th graders, and 10th graders have their own presentation. So I have like 4 students that are going to be switched off to another class, right? So check with your first period teacher, just make sure there's something like that. Right, so January 5th is going to be a mental health education day, and the 6th is going to be more mental health education day. I still have 2 days of mental health education. So there we go. So, that fun stuff coming up. All right, let's pick up where we left off on the midterm review, which is the last question you guys saw was this energy question. In physics, work is defined as force times distance, right? Force times distance. Okay. Really, it's the dot product of force and distance, which means you only multiply the parallel components together, right? Right, so if Nellie Newton pushes an object with twice the force for twice the distance, she does how many times the work? How many times? Yeah, 4 times. Okay. So work is equal to force dot distance. Maybe we'll call it like work initial work, right? So what if this new work by Nellie Newton is twice the force for twice the distance? Ooh, factor 2, is that 4 times force distance, which is 4 times the original work. Right? 4 times. Power is defined as what was power? Was that a rate of work or a rate of energy? How that work per time? Right, like that. Guys, what was the unit for power? So watts, right? Watts, right? So work is measured in joules, just like energy. It's energy transfer, joules per second. Joules per second will give you watts. Do you guys remember what if you have like an elevator being pulled up at a constant speed? Like, what's the power to pull it up? Okay. You could also rearrange this force times distance divided by time. You can get force times velocity. You could get that. So it's more obscure formula. Sometimes useful. The amount of potential energy possessed by an elevated object. Oh, well, do you remember the formula for potential energy? So I've been using the symbol capital U for this, for potential energy. Subscript G, gravitational potential energy. Does that go mgh? So the mass of the object times the gravity field that's in times some elevated height above some defined height 0 above a floor. Okay? You could say weight times height. How much further will a car traveling 100 kilometers an hour skid compared to one going 50 kilometers an hour? So in American units, that's going from about 30 to 60 miles an hour. But the important thing is that's increasing speed by a factor of 2. So you're like doubling your speed. Okay? So if you double your speed, what happens to your braking distance? Does anybody remember the answer to that question? Right here, let's work it out. So I'm going to do an energy setup, treating this as an open system. Okay, look like that. Okay. And the car initially had some kinetic energy because it was in motion. We'll have mv squared. Okay. Oh, throw a little subscript not, so initial speed. Let's say it's a completely flat terrain. There's no hills. So see if there's no height change, there's nothing to do with potential energy. Oh, now when the car brakes, there's some force of friction times stopping distance. Zaps energy out of the system. That's why it's an open system. Right? And the car comes to a complete stop. 0 joules of any kind of energy. No kinetic, it's not in motion. No potential, hasn't rolled up any hills. Right? And the relationship we're interested in is between this variable and this variable. Okay? Like if you double that initial speed, you see double initial speed squared is like 4 times the original energy. And that's gonna, well, the friction force is gonna be the same regardless of how fast the car is going. So that factor of 4 all gets routed into the distance. Okay, so just to boil it down here, initial speed squared is directly proportional to the stopping distance. So if you double the initial speed, you get 4 times the stopping distance. Okay, triple the speed of the car, you need 9 times the amount of road to stop. When as a pendulum swings back and forth, This pendulum. And in January, we'll go relook at this pendulum, and we'll look for like time period and length. Okay. So see this pendulum swinging back and forth. Okay. Ooh, is the height of the pendulum bob changing? Right. Yeah, the height's changing. Right. Is the speed changing? Yeah, the speed changing. But it's really fast here. It has really height here and here. Ooh, do you guys think it has a lot of potential energy at the ends and a lot of kinetic energy at the bottom? Right? And it's being transferred back and forth, isn't it? Do you guys think the total energy is constant, like as a closed system? Maybe the pendulum Earth system. Okay. Yeah, but I think we have potential to kinetic, potential, oscillating back and forth. When a car's speed triples its kinetic energy, okay, that kind of goes back to what we were talking about last question. Okay. So if you triple the speed of the car, wouldn't its kinetic energy go up by a factor of 9? Okay. And the follow-up question would be, well, you need therefore 9 times the road to brake. If the velocity of a moving object doubles, what else also doubles? Well, it wouldn't be kinetic energy because that would quadruple. Okay. Ooh, do you guys remember momentum? Mass times velocity? So I'm thinking that it would be momentum, right? So the kinetic energy would go by a factor of 4, but momentum, let's write this out. Momentum is mass times velocity. So if you double the velocity, you double the momentum. Richard? All simple machines ideally work on the principle that, we covered this in the PowerPoint the other day. You guys remember work input equals work output? Okay, so this is a conservation of energy, right? Energy is conserved. You guys remember rigging up those pulley systems? Okay. Now work is force times distance. So the force in times the distance in equals the force out times the distance out. Okay. And in your pulley systems, what do each of these represent? Right. So the input force was what the spring scale was reading. You're pulling on the spring scale. We got a little pulley system for you guys here. Okay. Say something like this. You guys see like a 3-to-1 mechanical advantage system right there. Okay. Okay, so here's the input force. Right? The output force is like the weight, right? The weight that it's lifting. Okay? And then the distances were, well, how far did each of these move? And that's where you like paid for your increase in strength because you feel really strong here. Wow, I need a little force to lift something really heavy. Okay? But I need to pull lots and lots of string. This only moves up a little bit. Like if I pull 3 meters of string, it only moves up 1 meter. Okay? So the principle that makes this work is that work input equals work output, and then everything follows from there. Okay? You can't amplify the energy in the universe. You can amplify your strength, but not the energy. How many joules of work are done on a box when a force of 25 newtons pushes it 3 meters? So work force dot distance. So we got 25 newtons, pushes at 3 meters. That look like 75 joules. 75 joules, do you guys think? How about if you lift a box that weighs 25 newtons and you lift it 3 meters? Oh, did 75 joules lifting it. How much power to do 40 joules of work in 5 seconds? I know power is work per time, right? The rate of work, rate of energy. So we're doing 40 joules of work, 5 seconds. Is that like 8 watts? I think 8 watts. Which has greater linear speed, a horse near the outside of the merry-go-round or one near the inside? And then there's actually a pair of questions here. Which has greater angular speed? So this is every time I break out this turntable. Okay. Ooh, look, I got 3 horses, 3 horses. Okay. Here's one really close to the inside. Here's one really close to the outside. Okay. Zoom out a little bit here. Right, give this thing a spin. Now, do all those 3 horses have the exact same angular speed? Are they all doing the same turns per time? The same revolutions per minute, same radians per second? Yeah. So angular speed is the same for all 3, same turns per time. But what about linear speed? What if I have a radar gun and I point it at each one of these individually? Who's moving the fastest? Definitely the one on the outside has the greatest linear speed. Back that up with an equation. You guys remember linear speed is equal to the angular speed of the whole disk multiplied by your distance from the center, okay, like that. So if you're twice as far from the center, you have twice the linear speed. If you whirl a tin can on the end of a string and the string suddenly breaks, what will the can do? So of the orbit of the can, here's the string, here's the tin can, it's going on. And then we're gonna cut that string. Is this tin can gonna make a last minute 90-degree turn and fly straight away? No. Is this tin can going to travel tangent to its path just in a straight line? Yeah, that's what I'll do. Okay. So tangent to its original path. Okay. I think you guys saw a question like this yesterday with like a planet around the sun and then the gravity turns off. It's the same idea, right? That's Newton's first law of motion right there. Newton's first law. Ooh, do you guys see a tension in the string? Okay. Guys, which direction does the tension actually pull on the can? Does it push it out of the circle? Does it pull it in towards the center of the circle? I think the tension, I'll go do F sub T, tension force, it's always pulling in towards the center. That's acting as a centripetal force, isn't it? Right? So does the centripetal force always pull in? Oh, the next question. Centrifugal forces, and notice that that's in quotation marks, right? Centrifugal. I almost never use that word in class. Okay? Are an apparent reality to observers in a reference frame that is what? Do you have to be in a reference frame that's rotating to have a centrifugal force? Okay. Now here, what if you were a ladybug on the surface of this can? Right? You're along for the ride, right? And the circle is like pretty big. Do you think you would feel like you were thrown straight outwards? I think that's what you would feel like. You would throw it straight outwards, okay? And that you could call centrifugal force. Okay? But from our point of view, see, we're up in a helicopter watching this from like third person perspective from our inertial frame of reference. Okay? We see that there actually is no force outside. There's only everything pulling in the circle, okay? Pulling inside. Similar idea if you're in a car making a left-hand turn, you feel like you're thrown towards the right side of the car. Really what's going on is you're trying to do it in a straight line and the car's like pushing you towards the left. A car travels in a circle with a constant speed. The net force on the car. Here, if this was a road and this was a car, is the net force always in towards the center of the circle? Yeah. If you want to say what's the magnitude of that force, you guys know centripetal force is mv squared over r. Okay. So the magnitude of the force would be the mass of the car times the speed of the car squared divided by the radius of curvature. The radius of curvature. Okay. And the direction of that force is towards the center of the circle. A wrench is slid spinning over a frictionless tabletop. Its center of gravity follows. Ooh, they're saying a wrench just as an example of like some weird shape. Okay. But you guys remember those foam boards that were also just cut to be like some weird shapes? Okay. And they had some center of mass. Okay. So this is really going to be like a center of mass question, center of gravity question. Okay. Now, if I rotate this and slide it over spinning over a frictionless tabletop, suppose I attach an LED light right here. Do you think that LED light would look all spirally? But what about the center of mass of the wrench? Would the center mass of the wrench just follow a nice straight line path, do you guys think? Yeah, and that would be the only point that does that. There's no straight line path, just the center mass. Suppose you just focus on that point. Would that center mass appear to be moving at a constant velocity? That would also be true, right? So constant speed on a straight line path, constant velocity. Right? That's the only point that would do that. And then in class, the sort of a similar example I threw at you guys was suppose you throw this in the air and it like flies through the air in a projectile. Right? This would follow a nice smooth parabola in that case, but on a frictionless tabletop, this nice straight line. Which of the following is the center of gravity located at a place where there is no mass? If you guys saw an option that said donut, that'd be a good option. Here's a donut, throw in some sprinkles, give it some mass right there. Do you guys think the center mass thing would be bam, right in the point where there's no mass, right in the middle of the donut hole? Do you guys think if you did that trick where you suspended it from a string, the string would hang right down through the center, regardless of the orientation that you hang the donut right through the center? Think so? An object will fall over if its center of gravity is. Ooh. Do you guys think if the center of gravity is not located above the base of support, it's got a floor? Oh, like you had like a pyramid type shape, and there's the center of mass. Okay, here is the base of support. The center mass is over the base of support, so that's going to be stable. Okay. But what if you had an object that was shaped like this? Okay. There's its center mass. Here's its base of support. Ooh, you guys see that the center mass is not over the base of support, so there's going to be a clockwise torque. It's going to fall over. That would be not stable. Do you guys remember the challenge I gave you guys? Can you put the heels of your feet back up against the wall and reach down and touch your toes? Right? Really hard to do. Some of you guys might be able to do it, but it's really hard. Right? Maybe not everybody. Right? Because usually that's what happens. You're going to get a torque and topple over. And an object thrown into the air with a spin rotates about its, you guys think, center of mass or center of gravity? It would spin about. A picture hangs on a wall from a wire that is passed over a supporting nail. The picture is in stable equilibrium because why? Get a picture of this picture. Okay. So the center mass of this whole picture and frame is pretty close to the geometric center, like right about there. Okay. Here could be a supporting nail. Here's a wire thrown over the supporting nail. Right. So here's the picture is stable, it's just hanging on the wall. Right. Now, why would it be stable? Let's think some reasons that could be. Right. Ooh, well, one thing I see is that the center of mass, center of gravity, is right beneath the supporting nail. Right. So that could be one reason. Right. How about this? What if I give it a little push down here and this whole thing rotates a little bit? I bet it would rotate about the nail. Right. Rotate about the nail. Might rotate about like that. And do you think that push it more and more and more? Do you think the center mass would follow like a circular pattern around this nail? Just like that? What if we push it the other way? Center mass would go like that. Okay. So if I release that force, do you think the picture's frame is going to go back to where it was? Ooh, that might be another indication that goes to the point that is stable. Okay. And do you guys also see how the center of mass is all at the lowest point that it could possibly be? I mean, water wants to flow downhill, balls want to roll downhill, and so it's already at the bottom of the valley. So I think that could be like a third reason that it would be in stable equilibrium. So different perspectives there. So that could be. Suppose you try loosening a nut with a wrench and the nut doesn't, oops, I skipped one. Torque. Torque is defined as, is torque equal to R cross F, okay, radial arm crossed with the force. Okay. Well, you guys know there's a wrench question coming up, and this is definitely applicable to that. So let's get a wrench going. Okay, wrench. I need a nut here. It's about like that. Okay. Okay, so here's say a radial arm, call that R, crossed with a force F. Good. Got like a counterclockwise torque. Trying to loosen that. Okay, so you try loosening a nut with a wrench, the nut doesn't give it at all. You increase your chance of success if you. Okay, I can think of 3 things you can do. Do you guys think you could push as hard as you can push, increase this force? Yeah, that'll definitely help. Ooh, do you think you could apply that force at the far end of the wrench versus if you apply it here? That's definitely not going to help. But out here, now it's getting more and more torque. Okay. You could even maybe extend the handle and get even more torque. And the third thing you could do is to make sure that these 2 vectors are at right angles to each other. About how I do it here. Is that's what the cross product means, right? You only care about multiplying the perpendicular components. The resistance an object has to changes in its rotational state of motion. Is that called rotational inertia? Right? You guys remember those 2 meter sticks I passed around a few weeks back? They had same weights taped on them, but at different locations. One of the weights were taped in close to the middle. So it's really easy changes to motion. Very little rotational inertia. The other one, the weights were way far out. And I went, I had a lot of rotational inertia. It's really hard to change state of motion. Something to do with MR squared. Suppose a huge rotating cloud of particles in space gravitates together to form a dense ball. As the cloud shrinks in size, it rotates. How? Okay. Is that going to be the same principle as the ice skater? Okay. So, what if an ice skater is just a giant nebula in space? Right? So, giant space cloud is like rotating a little bit slowly. Okay. And it gravitates closer together, just like this ice skater could pull her arms in. Once you like speed up spinning. And the principle here is that angular momentum is conserved. Okay? So I times omega. So if you decrease your I, you increase your omega, which is angular velocity. So spin really fast. I bet this space cloud is going to speed up spinning. A ring and a disk roll down a hill together. Who reaches the bottom first? That's this right here, right? Here's your ring. Here's the disk. Okay. Won't the ring always beat the disk rolling down? Related to rotational inertia. Newton had the insight to see that the all right, so what did Newton realize that nobody before him in history had realized? Did Newton was Newton the first person in history to realize that the moon was orbiting the Earth? Nah, not by a long shot. People have known forever that the moon is orbiting the Earth. Was Newton the first person to realize that the same side of the moon always faces the Earth? Now, people have known that since forever too. Was Newton the first person to realize that the moon orbiting the Earth and an apple falling from a tree were part of the exact same phenomenon? Yeah, that was what Newton realized that nobody before him in history had realized. Okay? That there was some kind of gravitational attraction that allowed for that type motion. Newton reasoned that the gravitational attraction between the Earth and the moon must be. Well, let's see what Newton came up with, and then we figure out something from that. Okay, so Earth, moon, there's the mass of the Earth, the mass of the moon. There's some distance between these 2 guys. I'll call it R. How about that? Like radial distance if it's orbiting there. Did Newton say that the gravitational force is universal gravity constant times the masses multiplied together divided by the distance squared? Okay. So I think the gravitational force of attraction would be directly proportional to each of the masses individually, and also inversely proportional to the square of the distance between them. Right. All those things would be true. Right. We're talking about center to center distance, of course. Center. Okay. If the radius of Earth decreased with no change in its mass, what would happen to your weight? So, read the Earth. Okay. Standing on the Earth, here's your mass, here's the mass of the Earth, and it could be the radial size of the Earth. Maybe I'll call it lowercase r because it's about to be variable. We're about to like squeeze this Earth in. Okay, see that? So your weight, which is a force, gravity constant, mass of Earth, your mass divided by radius of the Earth squared. Okay. So suppose we're squeezing in the Earth. Right? Now it's the same mass, we're just compressing it, making a little bit small, which means, okay, universal gravity constant is the same, the mass of the Earth is the same, your mass is the same, nothing in the numerator changes, it's all the same. But the denominator is getting smaller and smaller. Ooh, is what happens in a fraction when you divide by smaller numbers. The overall fraction gets what? Bigger. Bigger. So if you're standing on a scale, as the Earth is being compressed, is your weight going up, 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 up? Okay. Think so? Suppose the gravitational force between two massive spheres is 100 newtons. The distance of the between those is doubled. What's the force between the distances? Okay, so got like an asteroid here, and an asteroid here. Some distance between them. Okay. So F equals G M over R squared. So if you double the distance between these guys, guys, factor 2 squared, that's 4, and it's 1 over that. So would that be a quarter of the original force? And if the original force was 100 newtons, then what's the new force? 25, right? 25 newtons, I think. It's inverse square law, inverse square law. 1 over 2 squared is a quarter of the original value. By noticing that Uranus's orbit is perturbed, and by using the law of gravitation, 2 astronomers independently discovered, answer they're looking for here is Neptune, right? Although it's not actually exclusive to Neptune either, other planets too. But Neptune is one of these examples of a planet that was discovered mathematically before it was ever observed in a telescope. Right? So astronomers were looking at Uranus's orbit saying, hey, Uranus is not doing exactly what Kepler and Newton said it should do. Well, where would another mass have to be to cause this type motion? They pointed their telescopes to that part of the sky, and oh, there it is. So it's actually discovered mathematically. That was Neptune. Okay. Pluto, I think, was discovered the same way. The force of gravity on you is greatest when you were standing where? Ooh, I remember a few months back, took you guys on an adventure, the vicinity of the Earth. So here's the Earth, here's us at the surface. Okay. There was a graph that went along with this. We were looking at what is your weight as a function of your distance. So weight, I'll put force in newtons, as a function of your distance, say from the center. Okay. So I'll have some generic distance, lowercase r, okay, from the center of the Earth. Okay. And I'll use capital R to represent the fixed radial size of the planet. So I could be like right there, right? Now, all of us have spent our entire lives at the surface of the planet. So we all know that we have some weight right at the surface. Okay, so we got that point. That's the one we're all thoroughly familiar with. What if you dug a spiral staircase all the way to the center, okay, ignoring that it's all molten, yada, yada. Okay. Okay. Right at the center, would every single grain of sand pull you an opposite way? Which means you'd be floating around like an astronaut. So your apparent weight would be 0. Right there. Okay. What if you're like halfway down the spiral staircase? Do you think you would have half of your weight compared to the surface? There'd be a linear relationship here. And that'll be true if you assume uniform density all the way through. And actually, what helps prove that is you guys remember that spherical planet? Right? There's like an eggshell planet, I should say, a spherical shell. That anything above you in elevation would cancel out. So, like if you say like this guy right here, if there was a tiny planet just beneath him in elevation, everything above him is like a series of shells that cancels out. You can help show that. But then, what if you take off on a rocket? and you're flying away from the Earth. The further away you get from Earth, well, now inverse square law kicks in, GMM over r squared. So that's a 1 over r squared proportion. Looks like that. Okay. And do you guys see that the most you'll ever weigh in the vicinity of the planet is right on the surface? You guys remember this, right? The reason the moon does not fall into Earth is that, do you think that the moon has sufficient tangential speed? It's moving fast enough to the side? Okay. And back that up with equations. You guys remember centripetal force is provided by the gravity force. So mv squared on r is provided by g m on r squared. And the orbital speed you need is root g m on r. Okay. As long as you're going that speed, or ideally a little bit faster, then you can stay in orbit. Boom. According to Newton's laws, a rock and a pebble will fall with the same acceleration in a gravity field. Okay. Now, a big old rock and a little tiny pebble. Okay. There's a big old rock, there's a little tiny pebble. Okay. If I drop these, they'll fall together, right? No, they'll both accelerate, but they'll still fall together. This guy has more weight and also has more mass. And does the ratio of mass, there's a ratio of force to mass, is that the same for both objects? Yeah. Okay, so free fall gravity is weight divided by mass. Okay. And at the surface of the planet, it's the same for all objects at the surface. The value of acceleration due to gravity. So speaking of this, it's a big formula for this. Is it universal gravity constant times the mass of the planet divided by the radial size of the planet squared? GM over r squared. Okay, so I think gravity field of a planet depends on the universal gravity constant. It also is directly proportional to the mass of the planet, and it's also inversely proportional to the radial size of the planet, to the square of the radial size of the planet. All those would be true. The gravity field strength at the center of the Earth. Oh, we just did that with this guy right here. It would be 0, right? At the center, you have 0 weight. If you were to weigh yourself in an elevator that was in free fall compared to your ordinary weight, you would weigh. Now, if it was in pure free fall, do you think you would be floating around like an astronaut and have 0 weight? Right, that would be true, right? What if it was like partial free fall? What if it was you're just accelerating downward? Okay. You guys remember elevator physics? I think this was on the PowerPoint presentation too, right? Guy standing on a scale. Okay. So here would be the free body diagram. Weight down. There'd be a small force up. It'd be a small tension force in the elevator cable, or in the case of this guy, it'd be a small normal force reading from the scale. Right. And that normal force reading from the scale that he's standing on is his apparent weight. Okay. And that normal force reading from the scale ends up being m times g minus a if there's a downward acceleration of the elevator. So you would have a small apparent weight compared to your regular weight. A black hole is an object that, do you guys think has so much gravity that not even light can escape? It's kind of the definition of a black hole. By the way, if you shrunk down the Earth to this size, if you compressed the Earth to this size, so if you put all the mass of the Earth in like this right here, it'd be pretty close to getting to a black hole. Schwarzschild radius size. If the sun were to collapse into a black hole, what would Earth do? Which, by the way, the sun doesn't have enough mass to collapse into a black hole. It has to be at least about like 3 times as big, right? But playing in terms of gravity. So we got a star. The star is being orbited by, let's say, at least this planet. Planet's going around, right? And I remember that the gravitational force between the star and the planet goes like this: gm over r squared, and that the orbital speed, suppose it's pretty close to a circular orbit, like square root gm over r, right? Which would be true. Now, suppose that the star collapses into a black hole. Okay? See what changes. Universal gravity stays the same. The mass of the sun, now black hole, well, that's the same. Mass is conserved. The mass of the planet's the same. The distance between the two is the same. Nothing changes in these formulas. So would that planet continue to orbit the now black hole? Yeah, just keep going around. Nothing changes in these equations. When a star collapses to form a black hole, what happens to its mass? Does its mass just stay the same? I think its mass just stays the same, right? it doesn't gain mass, right? It could gain density, lose volume, but the mass is conserved. The early bird communication satellite hovers over the same point on Earth's equator indefinitely because, oh, get a picture. So let me go this way with this. Okay. So Earth, equator, pole. Okay. So do you guys know anything in low Earth orbit? For example, the International Space Station in low Earth orbit. Do you guys know how much time it takes to orbit the Earth? Do you guys know how much time? It takes about 90 minutes, right? So if you combine orbital speed with the circumference of the Earth, it takes about 90 minutes, anything low Earth orbit, which is pretty close to how I've drawn in that picture, like, to scale. Okay. If you go all the way out to the moon, which is like way the heck out here, right? All the way to the moon, does the moon take like 28 days to go around? Ooh, so see, like the further away you are, the more time it takes to go around. Do you guys think that there's some point right about here where it could take exactly 24 hours to orbit? 24 hours? And if it did take 24 hours, what would that look like from the surface? Suppose you're standing on the equator, you're looking up in the sky. Would it look like it's just hovering above you all day, every day? I think it would, right? If it took 24 hours to go around, that's one popular place to park satellites, right? 24-hour orbital period. It's called a geostationary. Compared to the period of a satellite in orbit close to Earth, the period of a satellite in orbit far from Earth, right? Well, I have 3 satellites here, right? 2 artificial and 1 natural. Right? So 90 minutes, 24 hours, 28 days. You guys see the further away you get, the longer it takes to orbit. Right? Further away, the longer it takes to orbit. Where does a satellite in an elliptical orbit have the greatest kinetic energy? So elliptical orbit, greatest kinetic energy. Let's do an extreme ellipse. Let's do a comet going around the sun. Be like that. Right? So the comet could be here, it's comet tail, and then comet here. So this could be the, it's called the perihelion, and here's the aphelion, right? This comet's going around. Now, when it's really far away, it doesn't have a lot of potential energy, but it's moving very slowly, so it has a little bit of kinetic energy. But when it's close to the sun, not very much distance means low potential energy, but it's also moving really fast, so it has a bunch of kinetic energy, right? Wouldn't that be true? Hey, if you added these two together here versus if you added these two together here, is the total mechanical energy the same at all points in the orbit? Yeah, the total energy is the same for the comet sun system, right? But the individual makes it, yeah, so the individual will change. Okay. Acceleration is defined. Okay, so these last few questions, just skip through the semester here. Acceleration is defined as a change in, is acceleration a change in velocity per time interval? The rate that velocity is changing? That's the, it's the original way you guys saw acceleration, right? 2 gliders have the same mass and speed, move toward each other on an air track and stick together. After the collision, the velocity of the gliders. Ooh. So mass, speed, mass, speed, right? No, same speed, opposite direction. Right? And they're going to collide perfectly inelastically. Do you guys think that the final velocity is just going to be 0? It's going to just come to a dead stop. So there's only 0 momentum in the system collectively ever. Right? This might have positive 3 units of momentum. This could have negative 3 units of momentum. Stick together, 0 momentum, 0 final velocity.
Would it not at the end have gravity affecting it though?
I think it says on an air track. Yeah, air track.
Okay.
Yeah, so frictionless air track. There you go. Machine puts out 100 watts of power for every 1,000 watts input. The efficiency of the machine is, so you can use the Greek letter eta for efficiency. You guys think you can do 100 watts output for 1,000 watts input and call that, as a decimal, that'd be 0.10. And as a percentage, you could call that 10%. 10% efficiency, right? As long as it's continuous process like that. Potential energy is an energy an object has because of its, here's the localized version of potential energy, MGH. Right? There's also a universal form, but let's just hone in on this one. Let's see, mass matters, gravity field matters, its height versus location matters. Right? So like weight times height. Right? I bet if I saw a multiple choice option that said something about its height or its location, that'd be a really good option there. Right? Nothing to do with speed, right? As the rotational speed of a space habitat increases, the apparent weight of the people inside. Ooh, let's go to an O'Neill cylinder. That's what we're talking about. O'Neill cylinder. Let's get this thing rotating about this axis. This is the center of the whole thing. Here, I'll throw a ladder across the middle. Some rungs. Okay. We got here, it's spinning like this, maybe omega for angular velocity. There's a bunch of people. Okay, right? And all these people have an apparent weight. Okay? Do you guys remember centripetal acceleration? Now, in a linear sense, one of the first ways you guys saw this was v squared over r, but there's a more useful equation for O'Neill cylinders, which goes like this. Centripetal acceleration is omega squared times r. Okay? So if you speed this up spinning, suppose it's spinning like 3 times as fast, right? 3 times the angular velocity. Would that be 3 squared is 9 times the centripetal acceleration, right? So 9 times the normal force from the wall holding them in, 9 times the normal force, centripetal force, and 9 times the centripetal acceleration. So it would feel 9 times as heavy, right? Right? Spinning 3 times as fast. So the faster it spins, it's going to feel heavier, heavier, heavier. Okay, guys good there? All right, who's got any questions? Anything about this? All right, so I think you guys been paying attention, taking good notes for the last few days. I think should be in pretty good shape for the midterm.